Great. So let's get started. It is my pleasure to introduce Jon Peterson, who I guess you've seen is Jon Peterson. So he's a member of the Internet Architecture Board, the board that sort of governs the intersection of technology and policy for the Internet. He used to be a member of the IESG, so the folks who actually say, yes, this could be an RFC, or no, it can't because you made mistakes. He's written a whole host of RFCs. Probably the most significant one would be SIP, the Session Initiation Protocol, which is the basis for a lot of IP telephony today, as well as instant messaging, presence, and a lot of other online services that kind of emerged in the early 2000s. So I met Jon actually when I was a freshman in college, way back when, and he was studying basically technology and literature as a graduate student at BU. And since then, he's gone on to greatly influence and change the internet. So without further ado, I would encourage you to ask questions at any time. And there will be a little bit of time at the end for questions as well. And so without further ado, Jon.
Thank you, Phil. Everybody hear me? Does this work? It should be up a little. Yeah, I wish I really could say that I greatly influenced the internet. Well, that would be really great if that were true. But a lot of what I have to discuss today actually is the problem of internet governance. And I'm fond of saying that the term internet governance is a kind of an oxymoron. So you can see my talk is called Governing an Internet. But what does it really mean to govern an internet? What kinds of controls do we actually have? That's kind of what I'm here to talk to you today about. And I'm going to talk about it in the context particularly of IP addresses. And many of you have heard, I understand, of the crisis with IPv4, the apparent necessity to transition to IPv6, and the wonderful corner that we have backed ourselves into as we try to effect this transition. And to me, this is really kind of a poster child of, especially kind of in the last 10 years, as the internet has grown from, an interesting commercial and research network into the dominant portion of, a huge swath of the people of the world's lives. Our ability to affect changes like this has unfortunately been dramatically reduced. But to start off on talking about the internet, we first need to get into what the internet really is. A deceptively tricky question. We shouldn't really laugh at Ted Stevens when he calls it a series of tubes. Somebody wrote a book about this actually recently, I forget the guy's name, but who looks at the actual tubes that make up the internet. I spent a few years in the global architecture group at level 3, and I can tell you, there's a series of tubes that you lay into the ground, usually alongside of railroads, and you put fiber optics into them. There is a series of tubes, and that's one way to talk about what the internet is. There's also, of course, the smarts used to route things between tubes, the routers that sit on the ends of those tubes. And controlling them is one way you can kind of govern the internet, perhaps. Then, of course, there's the companies, the people like Level 3, AT&T, Verizon, the people who actually are responsible for operating all of that equipment, moving things around. Is it their agreement that really makes the internet what it is, their consensus that makes the internet what it is? And then finally, there's a stack of protocols. And in the Internet Engineering Task Force, where I've done a lot of work in the last decade or so, obviously that's our primary concern. And the protocol that the IETF has responsibility for that probably is most essential to the operation of the internet is IP, is the internet protocol. But for our purposes today, given that there's many different ways to kind of slice up what the internet is, to me the internet is an overlay that sits over a diverse set of physical networks that has this property that if you have an internet protocol address, well, you can have data sent to you from virtually anybody else who's on the internet. Arbitrary data. Doesn't really matter what it is. And that is kind of what defines the internet. Everything we do with the internet is based on that principle being true. And IP for this serves as kind of the glue that binds together those lower layer networks to the applications. You can see here a depiction of the famous waist of the hourglass picture that kind of shows IP in the middle where things get very narrow, but there's a whole cone of different physical networks and layer 2 transports that run underneath it. And then, of course, a host, now an immeasurable host of applications that actually run above it in its session layer transports. OK, so if IP is the critical piece, who controls IP? It'd be great if there's a really straightforward answer to this, actually. If somebody just controlled IP, we probably wouldn't be having these discussions about a crisis of managing IPv4 and IPv6. We can tell you who invented it. I'm sure you've been told already about Vint Cerf and Bob Kahn, the relevant RFCs that have specified this, and all the things that end up running on top of that fantastic work. Now, originally, back when the internet was just kind of a research project, when mostly just some academics cared about it, there wasn't really any commercial interest yet, Jon Pe took care of it. he helped hand out the address blocks. There was actually an RFC that would be issued periodically before there was any governance structure of the internet. They would just kind of list like what the IP addresses were that were attached to what hosts. And the network was so small, it was feasible to just keep track of that and distribute it as updates periodically. And the architecture, insofar as there was one of the internet, well, there was a guy named Dave Clark, who's now at MIT, great guy, who was the internet architect. Now, once the internet got big enough that you kind of needed more than one person to worry about that, they created this internet architecture board, which is part of what I now sit on, that among other things has responsibility for this mess of IP address allocation. So I assume everybody here has heard that the v4 space is having a slight problem. That's something that we've all discussed here before, I'm sure. However, v6 has yet to become mainstream. And I'll be talking more specifically in numbers and graphs of what I mean here by mainstream in a little bit. But to the internet stakeholders, to the alphabet soup of organizations like the IAB and the ITF, and I'll tell you about a bit more as we go on here, we have a tremendous amount invested in v6 working. And it is to our chagrin and utter frustration that we built this great v6 system. We have this clear problem that it seems to solve. And yet, kind of what that middle step is, that question mark, question mark, question mark before profit in this particular graph, we have no idea what it is. And we in the IB, where I've sat the last 4 years, one of the things we do is we're responsible for the administration of the protocol parameter values managed by the IANA, by the Internet Assigned Numbers Association, which these are the people who actually give out the big blocks of IP addresses to the regional internet registries. So this kind of ends up on our plate and on IANA's plate. And if we can't make it happen, who can? Who's really responsible for making this happen? So as you can see, it's actually pretty straightforward. There's only a small number of stakeholders that have a relatively simple set of interactions that we need to take care of in order to be able to solve this problem. Sure, it all does seem to centralize up to IANA, who is paid for by ICANN today. But below that, of course, there's the Department of Commerce's influence over both ICANN and the IANA. There's all the regional internet registries. You see there Afrinic, RIPE, ARIN, LACNIC, and APNIC listed. The root server operators who operate the root of the DNS. It's absolutely essential that they buy into this because there need to be specific DNS records for anything to work with IPv6 on the internet. The governments, the businesses, the individuals, and then, of course, people like the ITF and the IB. This is kind of why it's hard to affect change these days. This is a little different from the model where Jon Pe just kind of gave you a domain name or gave you an address. We're in a different world now. And it's important to remember when we think about this, the time that v4 came out, basically we were assigning large numbers of addresses already in the 1980s. The young internet lived in a very different world than our world. It lived in a world of mainframes. There weren't all these proliferation of PCs, let alone laptops, let alone mobile devices, let alone tablets. There were a very small set of systems out there that actually required an IP address. For the most part, if in an academic environment like this, you'd have a terminal, perhaps a Stanford University network terminal, actually, come to think of it, that would let you connect up to some mainframe. And that mainframe, of course, would have an IP address and would communicate over the internet with other similar systems. But none of those terminals necessarily needed to have their own addresses at that time. So the 32-bit IPv4 address space that was designed for this environment must have seemed just like overkill. Like you're swatting a fly, not with a sledgehammer, but with like a city bus. 4.2 billion addresses for, given the number of mainframes that are out there, obviously there's no way we could possibly ever exhaust that. And this thinking, we can align it with this apocryphal quote here that's often attributed to Thomas Watson about how there would be a world market for only 5 computers. And and this is supposedly from the 1950s if this was said. I've seen some proposals for who it was that actually said this. But in the ancient world, you didn't really think about there needing to be this many computers that would need IP addresses to start with. And so IPv4 was allocated pretty carelessly. Basically, if you wanted some addresses, you could get a pretty big block. For example, there's this one university called Stanford, which had a pretty small student body at the time, still does now, that was allocated a Class A, which we now call /8. In other words, 16 million and some addresses for its 14,000 or so.
Give it back.
I will attest the fact Stanford gave back certain resources and not others. We will get to that in a future slide.
MIT didn't, though.
MIT did. You've already seen this talk. Please do not steal my bits going forward, okay? And famously, this was not just Stanford that had a kind of cavalier attitude about this. The first chair of the ITF, Mike Corrigan, he actually just asked Diana for his own Class A. So if you're just one guy, and if you knew people like Jon Pe, you could just ask, and you probably receive. I went to a small liberal arts college as an undergraduate called Reed College up in Portland, Oregon. We didn't even have a computer science department, right? I mean, there were barely computers at the school. And yet, even we would get a /B, a set of 65,000 addresses, vastly greater than a student body could really require at a place like that. And of course, the smallest block that people gave things out in back in the 80s was the Class C, which is only 256 addresses. So given that we're handing these things out in such a cavalier fashion, depletion pretty quickly became a concern, actually. So this is a slide that was put up in the ITF in 1990 at a plenary that first actually predicted, if we keep giving things away at this speed, we're going to run out of Class Bs pretty soon. And you can see the dates there. They go into the 90s, and they talk about the various organizations that held these at the time, like the NSFNet and BPN, who are protagonists in the development of the network then. And it looked like by 2002, we'd be in a place where the Class B address space would effectively be depleted. So we've known for a long time, in other words, there was going to be a problem. And this reflects all of the realities that I was talking about earlier. The internet had grown up. There were so many more devices that wanted to get on the internet by the early 1990s, and there was the commercialization. The NSFNet would soon be sold as a backbone, actually to AOL at the time. But in this environment, it became clear you needed more stakeholders than just people like Jon Pe and Vint and a few propeller heads in the Internet Architecture Board to figure out what you're going to do with these addresses. And it was around this time that the regional internet registries were created. People like originally Internic, RIPE, NCC, and AppNIC. Have you talked already about kind of RIRs here? OK, good. So if you're all familiar with kind of who the regional internet registries are and what they do, they take the address blocks from IANA and hand them out typically to end users and companies. ICANN was created, in the late 90s to be a successor to Internic and to manage the domain name assignments. ARIN was formed in 97 to administer all of the IP addresses for North America. And Jon Pe was originally on the board, but obviously it was no longer a situation where a sole person could take responsibility for this and distribute these addresses in an equitable fashion. And people really started to care about who owned which addresses around then. Addresses had started to become precious, and with that there came a host of kind of security concerns that I'll be talking about going forward. One of the most immediate concerns from an internet governance perspective, when we try to figure out how to make the internet better, which typically means how to make it fair, how to make sure that everybody gets a fair share, is that this was not a party to come late to if you wanted internet addresses. If you look at this graph, you'll see that ARIN, the red line I'm showing here, has vastly greater amounts of IP addresses than, say, Europe did or the Asia-Pacific region did. And this is even worse when you realize that LACNIC and AFRINIC originally were part of ARIN. They were only broke out much later. So you have to imagine both the yellow and the purple bars there added on to the end of ARIN to really get a picture of what this looked like originally. So don't come late to this party. This created one of the great crises of the digital divide, which today still dominates a lot of the discourse about how we should go forward with address policy, because it was disproportionately favorable to the people who came first, and that happened to be really North America. OK, so you've got a problem. We know depletion's coming. We know things aren't super fair. What do we do? Well, the first thing we do is to try to find conservation measures. And IANA has been implementing these for some time, since the early 90s, really. The most important of these was probably classless interdomain routing, or CIDR. And whenever you see this notation, the /8, the /16, the /24, those are CIDR notations. And they reflect the fact that instead of the 3 original classes, well, actually there were 5, but 3 that were important, original classes, the A, B, and C of addresses that were allocated, under CIDR you could give much more narrow blocks. You could pick a block that was actually tailored to the needs of a particular enterprise or an organization. And so no longer would you be giving Stanford, say, a Class A, which is clearly more than they needed. And as Phil rightly pointed out, in 2000, Stanford did return their Class A as part of these conservation measures. IANA was really going around at the time and knocking on doors, saying, so we noticed that you've got these addresses. Could you show us what you're actually doing with them? And are they actually being propagated? Are they being advertised as prefixes on the internet? If not, there are other people who kind of need them at this point. It'd be great if we could have them back. So Stanford gave you back a class A and only took 5/16s, 5 class Bs in return. So 300,000 or so addresses. But again, you are one of the good citizens in this regard because MIT kept their /8 and also has a ton of other resources that they're still holding on to. Really, the worst of these resource hogs, of course, is the Department of Defense, and we can talk about what their allocations have been. But at the, oh, sorry.
Sorry, so it says MIT kept their /8 and now has 2/16s and several /20, so they got more?
Yeah, so they had a lot of that.
Could you repeat the question?
Oh, I'm sorry. So the question was, isn't MIT being extraordinarily greedy, and not only did they keep their /8, but have actually since accumulated some /16s and /24s. So they had some of those originally as well, and as did Stanford. Stanford had more than its original class A, but I think actually one of the class Bs that MIT got, they have gotten since. But they're cordoned off for kind of special projects. When you talk about what MIT is, obviously it's a very large and diverse organization like Stanford. There are different schools and laboratories and so on. I think one of those class Bs was from Lincoln Labs that they got later. So I mean, individual labs that had their own needs kind of needed to administratively get something separate. But the important thing to get about CIDR, very important technology from a conservation perspective, but it did make routing in the internet a bit more complicated. When you're just making routing decisions on a /8 on a class A level, well, there's only one of 256 choices of where you send your traffic. To build a router to do that's pretty simple, right? The finer granularities you use, the more complicated the tables are that the routers have to rely on to make forwarding decisions. And so there became a pressure from this on getting the core routing table to be manageable, to make sure that you could actually make a routing decision quickly, that you wouldn't use much power. And people at companies like Cisco and Juniper spent a tremendous amount of time as CIDR became more and more implemented, trying to figure out how to resolve that. So this is a picture of what the BGP advertisement space actually looks like today. And the blue that you see here is prefixes that have been assigned and are actually being advertised. Interestingly, the orange that you see is prefixes that have been assigned and are not currently being advertised. So even with the conservation that I've been describing, it's actually about a quarter of IP addresses that are currently assigned are not actually being advertised by anyone still today. And this shows you limits of conservation. And people who do science about namespace allocation and so on will tell you, with any kind of namespace that you especially have in a distributed system, I've heard that about 30% waste is close to the logical limit you can actually get. It's very difficult to design namespaces that are distributed in terms of delegated down through multiple layers, where your allocation is actually going to be better than that. Nonetheless, it does paint a pretty grim picture of what the limits of conservation are. So conservation's not enough. We recognized, oh, I'm sorry.
What was the IR pool on the previous slide?
IR pool on the previous slide. So the
RIR.
So the RIR pool are things that are still being held on to by the RIRs themselves that they have not yet assigned. So they've come down from IANA to the RIRs. The purple on the side is stuff we in the ITF are hogging. Actually, a lot of this is for either future use. Some of it is for specific protocol functions, things like Anycast and some multicast addressing, loopback addresses. All the things that are kind of defined in RFCs and set aside are in that huge block. And they're a whole other category of waste, depending on how you want to look at it. But we, for example, just allocated a new /10 out of that for a specific class of large-scale NATs, which we might be able to talk about if we have the time here today. So we know conservation's not enough. What do we do? Well, again, the ITF, we're fond of solving engineering problems with engineering. So some people sat down and said, problem is not enough addresses. Great, we'll make more. We'll go back and revise the IP standard. We'll have a thing called IPNG. Yes?
So you mentioned that CIDR will increase the complexity of routing tables. Will IPv4 do that to an even more extreme level?
You mean, will IPv6?
Yeah. Can you repeat the question?
Yeah, so I'm sorry. The question is, will IPv6 also increase the complexity of routing decisions that are made in routers? To some degree, although IPv6 today, and I'll talk about this in a moment, is being allocated in very large blocks, kind of like the classic Class A situation was. Pretty much the minimum allocation you'll get from an RIR is a /48. Which is 18 quadrillion addresses, enough that you can pick addresses at random and you'll be fine. So the decision that's being made in the routers, is at the /48 level for the most part for v6 routing. We'll get back to that in just a sec. The point being, yes, we decided the right way to solve this problem is with engineering. We'll build a new version of IP. And we're going to do it. We're going to make so many addresses this time. OK, we were wrong. 4.2 billion was going to be enough. So this time, we are going to make sure there's really, really enough addresses. Now, I'm not going to try to say this number. I know it's 340 undecillion. It's a lot. So again, they're grouped into /64s, 4/48s, but the /64s into these 18 quadrillion address blocks. IPv6 fixes the network prefix at 64 bits. So basically, again, this is the minimum allocation you're going to get. Now, I don't expect that Stanford is ever going to have a need for this many addresses, for example, but that's what you're going to get when you get IPv6. There are enough addresses that you can choose the names for them very whimsically, as you can see from the examples here. Freenet using Dead Beef Cafe as one of their addresses. Cisco, that's actually supposed to spell out Cisco dog food, the DO6 dog, Cisco dog food, and it's from eating their own dog food. At the IETF, people actually went around with shirts with this address on it. If you go to it, you will get a Cisco page, a Cisco web page that talks to you about IPv6. Facebook, you can see as well, has that Facebook with the C on the end. So there are so many addresses, you can squander them in any way that your imagination would like you to do so. It's also the case, it's not merely about having more addresses. Building in IPsec from the start into v6 is something people thought was very important. However, a new standard like this can't just be introduced overnight. You need some kind of interim strategy to get us from v4 to v6. So conservation wasn't working alone, so a decision was made to take some of that bucket of addresses that the IETF has been hoarding for itself. In this case, /A was called 10, as well as a class B that was called 192.168, and to turn them into private address space that you could use on internal networks that didn't necessarily need to connect to the internet. And this started up around 1996. So this was part of this same set of measures when people realizing conservation was failing around the same time that v6 started up is when private address space was first created and allocated. And I still remember very vividly around 97 compiling into my Slackware kernel the IP masquerading function that would let multiple computers in my network be able to play Quake with the internet at the same time. It was like a really amazing idea. I should have turned my phone off before I did this, of course. But today, of course, this takes the form of the ubiquitous router that's in everybody's house that we know acts as a network address translator. I'm sure your videos have gone over what network address translation is, but moreover, you're all familiar with it because you can't escape it in the world today. You have private addresses in your house based on these address ranges we created at the IETF, and they are switched around by this router device and put into a format that allows multiple computers to kind of hide behind a single router. And what this has created is a slightly different world than the end-to-end model for which the internet is famous. It's created what I consider to be a three-tier world. There's a world of home nets, a world of an access network, and then the world of the default free zone of the internet. And in the home net, you use one style of addressing. All that sits behind the router. Then in the access network, you probably there have a public IP address, but all that needs to go out to a border router, which is where BGP is ultimately spoken externally, and you learn how to route things when you don't have a default anymore. And this has been an interesting world in the sense that it has given us the tremendous advantage of staving off v4 exhaustion for a couple more years. But at the same time, it's a trade-off. It's a trade-off for many sorts of applications that actually want to rely on those end-to-end principles. Any applications that need to be able to talk about IP addresses themselves, well, the NAT usually isn't smart enough to know what it has to change inside of packets beyond just what's in the header. If you're going to be talking about, say, setting up a rendezvous protocol like SIP, which Phil mentioned I'd been involved with earlier. But this really makes protocols like the protocols that underlie Skype and BitTorrent marvels of engineering, and that they figured out ways to integrate this in with these NATs and to make sure that they'll still work despite the fact that this address translation is going on. Because ultimately, this address translation was optimized for the common case of the internet. I want to send email. I want to be able to access a web page. All things where something's starting with your client and then reaches out to a server in the public internet. But nothing really works where something out in the public internet needs to reach you anymore. So that definition I gave at the start of this, if you have an IP address, other people can send you arbitrary data. Well, not a private IP address. And this is both a feature in the sense that it has a security function. It acts as a firewall, and a pretty damn good one. But also a significant detriment to a lot of different applications. So this bought us some time, but not much, because Judgment Day was coming. There was no way that these conservation measures and NATs were going to stave off the inevitable. So the IANA, as I said, is the font of address allocation. They give out the addresses to the RIRs. Well, their final assignment rule was invoked more than a year ago now, February 3rd of 2011, which basically said when they were down to only 5/8s left, they would give one each to each of the 5 RIRs. And that would be it. And IANA is now out of the IPv4 allocation policy. And to give you a sense of how rapidly these addresses were being consumed by the RIRs at the time, that was February 3rd. By April of 2011, AppNIC was already out. As they'd gotten that last allocation, they were already out within 2 months of that time. This year, and actually not too long ago now, just on September 14th of 2012, RIPE ran out. Now, when I say ran out, what I mean is they've gone below having a single /8 left in their RIR pools. When we were looking at the RIR pool earlier, those RIR pools are getting smaller and smaller. They still have some residual things they can hold on to, but not really enough to be able to handle serious requests for allocations anymore. And the rest of the RIRs will follow in the next couple of years. ARIN and LACNIC, they have 3/8s left each. AFRINIC has 4. So it's a good thing that V6 is here to pick up the slack, right? So how are we doing with V6? So this is a graph that shows the percentage of internet traffic as monitored by Arbor Networks that is actually V6 traffic. And as you can see, this is kind of between 0.1 and 0.2% of internet traffic is now V6 traffic. So Houston, we have a problem. This was 16 or so years of work. 16 or so years ago is when V6 was created. And what have we accomplished in the intervening time? We've gotten to a point where V6 is between 0.1 and 0.2% of all internet traffic. This is not good. Now, the problem isn't that it hasn't been widely implemented. Every device that someone's holding in this room, I'm willing to bet, supports IPv6. You would, if your DHCP server was offering you V6, you'd be getting it on all of your laptops, all of your smartphones, all your tablets. The core routing infrastructure supports it as well. It's not Cisco and Juniper's fault in the sense that those routers have supported V6 forever. Implementation, however, is not deployment. I mean, this is one of these critical questions about governance, right? What we do in the ITF is we create standards. And vendors implement those standards. They put them into the devices. That's why they're in all the things that you have. But it's a big difference between something being implemented and something actually being used. And how we cross that chasm is really one of the great challenges in the intersection of technology and policy. And to give you a bit of a spoiler from where I'm going here, I'm all ears if you have any ideas. I mean, at the end of the day, few last mile providers today offer V6. There are some, and I have some glimmers of hope to show you at the end of this, but it's relatively few. Oh yeah, and it's certainly not for want of people actually getting allocations of these V6 addresses. My own employer, Newstar, we have about 20 of these /48s. Yes?
What do you mean by last mile provider?
So, I mean, access networks, your Comcast. Oh, sorry. Yes, what I meant by last mile provider. So last mile providers, the access networks, the Comcast, the AT&Ts and Verizons, the people. Now, Comcast is an example of someone who actually does. There is actually some significant V4 deployment to Comcast customers in some markets. But it's relatively rare today that you can go to your ISP as a residential customer and say, I don't want to get IPv4 addresses from DHCP. Give me V6. Some you can, but not many. And as I said, the problem is here that time's really running out. So this is the model that shows where we're headed for depletion with those remaining 3/8s that ARIN and LACNIC have and the 4 that AFRINIC has. You can see where those graphs go down. And, well, it looks like in 2013, we're going to run out of 2 more, at least. AFRINIC will last a little longer than that. So we spent a decade struggling with this. We can't turn V4 off. Like, no, there's no internet police. The IAB and people like us, we can't just make this happen. So most of the transition strategies that are being considered for this involve some form of dual stack. We're going to have V4 and V6 coexist in some form. However, dual stack turns out to be not so simple. And a lot of the studies that have been done in the last 2 years especially, and there have been pioneering things I'm going to be talking about in a few moments, that have kind of looked at how serious these problems are. Just because you have a V6 address doesn't necessarily mean that you have connectivity to another v6 address that's out there in the world today. And this is because the backbone, as it were, for v6 is not quite as pervasive as the one that we're used to from IPv4. You really have to think of these as two different overlay networks sitting on the same physical infrastructure. But in one case, the kind of backbone goes everywhere. In the other case, it's kind of spotty. So even if, say, the DNS tells you that some particular host you're trying to reach has a v6 address, and you might have one too, today, there's still no guarantee that you're actually going to be able to connect to one another. There's lots of islands of v6 that are deployed out there. And getting around that and even discovering that that's true is a serious problem. But the biggest problem isn't really technical at all. So this is our audience participation component of the talk, our kind of little Price is Right that we can conduct here. We ask what you can buy for $11.25.
The domain name for a year?
A domain name for a year, that's a good one. You can probably get it even cheaper than that if you try to these days.
Dinner?
Dinner? Not anywhere I'd want to eat, but... So the answer is an IPv4 address, actually. And the precedents for this, if we look at them, are that in March of 2011, there's a company called Nortel, who used to be a big player in telephony equipment space back when telephony equipment was something you could make money from. They went bankrupt, and they ended up selling their entire allocation of IPv4 addresses, which they had accumulated. They sold to Microsoft as part of their bankruptcy filings for $7.5 million, or in other words, $11.25 per address. In December of 2011, just a few months later, Borders, similarly going through a bankruptcy. Well, it turned out that they'd gotten a Class B back in the day. And yes, they chose to monetize it. At $12 per address, they got a pretty decent amount of money for it then. But let's look at that a little more closely. Did Nortel pay for those addresses when they got them back in the day? Probably not, actually. Anybody who got them early didn't really pay anything. They just asked Jon Pe. Like Stanford, when it originally got its Class A, I imagine they didn't pay $188 million for it. I think they just asked for it, and they got it. So now IPv4 is becoming something of a business of speculation. Now the domain name business has been like this for some time. You might be able to get just any old domain name for $11.25, but I know a friend who happened in the, well, I guess it was probably around 1990, to ask Jon Pe for domain.com. Just, he was going to run some information about domains on some website he was going to put up there. When, say, 2000 came around in the height of the .com bubble, he'd gotten a number of bids for it and managed to turn it around for $1 million. And he paid nothing for it. He just asked Jon Pe. He got it. Turned it around by holding on to it for $1 million. This is what the world was like back then. And this is, unfortunately, the world it looks like we're entering into with IPv4. And these are just economic fundamentals. It's no coincidence that you see deals like the Borders deal and the Nortel deal so soon after Judgment Day. It's a supply and demand question, but more importantly, once something has a value, the entities that own it will protect that value. And this is such a critical part of the story of how difficult it is to transition to from v4 to v6. I want to say it again. Again, once something has a value, if you have some of that stuff, you don't want that value to go away. If you're paying millions of dollars for IPv4 addresses, what is your incentive to see that value destroyed by there suddenly being so many addresses that they could never possibly have any value? And when you ask yourself, who needs to be incented to transition to v6 really? Well, if it's the same people that own v4 addresses that would be taking a write-off of potentially of a ton of money if they had to transition to v6, well, those people seem to have an incentive that's entirely contrary to v6 actually working. And that's a fundamental thing to understand about this. The economics dictate this much more than the technology does. And we see this today in the emergence of actual commodities markets. And there are a ton of them. There are sites out there like Adrex, Accuro, IPv4 Marketplace, Trade IPv4. And here you can see bids and asks on IPv4 addresses. This is a snapshot from just like 2 weeks ago. And it's not just onesie-twosie things. /8s have been advertised for sale through these things. And as you can see here, the prices are not bad. That's Phil.
Who's /8?
Yeah. I'm not at liberty to disclose that. But yeah, there are /8s out there that have actually gone on the market in this regard. And a ton of /Bs that have as well. So these things are now valuable enough to steal at the end of the day. Ownership of address blocks, unfortunately, has never been strongly coupled to routing. When you do BGP, you basically just say, please advertise this prefix, and other people believe you, right? And send traffic into the direction of your AS because you said this prefix is home to this AS, please send stuff here. And having worked at a carrier like Level 3, I can say that if you're a backbone provider, a Tier 1 provider, well, people pay you to advertise prefixes for you. And that's really your only question is, you're paying me, right? OK, great, I'll advertise that prefix. Thank you very much. And this has led to a culture in which there have been plenty of kind of what we call dark blocks that have been controlled by hackers and spammers. It's become a serious security problem. If you take anything of that 25% that I was showing you earlier of addresses that are assigned but are currently not being propagated, not being advertised on the internet, well, those are things you can squat on. And the favored people who squat on those are spammers. They'll use those IP addresses to send massive amounts of spam out to public relays from them in ways that are virtually untraceable. This has become a very fashionable practice for spammers and for people who spread malware alike. And this is a significant weakness of the global internet. Yes?
Why does squatting on them matter versus trying to spoof some legitimate IP address?
Good question. I mean, in order to... Terrible at this. Yeah, so the question is, why does it matter squatting on an IP address block versus actually spoofing an IP address block that is actually advertised? I think a lot of it comes down to when you're advertising this in BGP, if you need to have any kind of return routing, obviously, then it's not going to work to do spoofing. And some of these email things do actually involve challenges these days of various kinds. So you need it for that. Some people also do reverse resolution before they accept email. We could talk as well about things like DKIM or other strategies that spammers are now trying to get around before they send traffic. But I mean, at the end of the day, it's the return routability principle that makes you want to be able to advertise the prefix itself. And although you can advertise a prefix that conflicts with an existing advertisement on the internet, people do this too. And there's at least one case I'm aware of where for what apparently seems to be a state actor hijacked a BGP prefix in order to capture traffic that was associated with an international VIP to send that through a particular part of the world. Unfortunately, this strategy has become legitimized by the way that Anycast works, where you can actually have multiple advertisements from BGP for the same home, or multi-homing in general. So it's very difficult today to be able to map what the right AS is for an IP prefix to be sent to. So people think we need to fix this. And the way that people propose fixing this is something called the resource PKI, or RPKI. And the idea here basically is to certify the assignment of address blocks. And this starts at the IANA level, but really is implemented today since IANA is out of v4 addresses at the RIR level. The RIRs are generating certificates that they're issuing to people that are owners of address blocks that let those owners prove that basically this prefix is supposed to be advertised by the following autonomous system. And the goal eventually is to have this integrated into the way that BGP operates, so that you will no longer accept an advertisement for a prefix unless it has a signature that you can tie back to the RIR in order to prevent both the squatters who just want to be able to spam from dark address blocks, but also prevent the hijackers who want to be able to steal vast swaths of traffic and get it to go to nation states where it probably doesn't belong. And all this, of course, has real implications for the commodities market that I was just describing. Think today about how informal that system really is. And who owns the block? Today, for the purposes of BGP, nobody really knows. So if I had a Class B and I sell it to you, there's no real paperwork that needs to be exchanged in order for you to advertise that over BGP. I withdraw the advertisement, you put in a new one, we're done. That would really change here. Now the RIRs would have to be involved in our transaction. And this, too, is going to change the dynamics of these commodities markets quite a bit. And this is a relatively new concept. I think there are about 8,500 or so prefixes that are actually signed with RPKI today. And no one is really using it to authenticate BGP advertisements today. But they will. And this is just kind of a model of what this really looks like from a delegative perspective. And you put out a route origin authorization that shows what the specific autonomous system or autonomous systems are that you want to have associated with the prefix. For cases like multi-homing or Anycast, you may actually want to have multiple prefixes that are, multiple ASs that are associated with the same prefix, since you just want to find the kind of least cost route to get to them. Exciting stuff. right? Sounds like it really solves a great problem. It improves the security of the internet, prevents these awful spammers from doing what they want to do, but it also really kind of just defends the value of v4 even more, right? I mean, nobody wants to steal v6. But this is a mechanism that, once we put it out there, is making the administration of v4 much safer. And again, is solidifying that value. It's making it harder to get rid of v4. And this is another classic example of the trade-offs of governance that are so difficult for us to grapple with as we look at global standards. Really, what's the right path? There are such problems that motivate this. The hijacking problem and the squatting problem, they're serious problems in the global internet. You know, at the same time, by fixing that hole, we're just kind of further cementing a v4-centric world. We're creating more incentive for things to stay the way that they are. And yes, there are a lot of operational things I won't actually go into today about this that make it tough. But at the end of the day, you know, the classic innovator's dilemma, if you need a bunch of address space today, let's say you're an Asian mobile carrier, you're adding 15 million subscribers, so in other words, a /8 worth of subscribers like per year. You know, do you really have any option other than to go to v6 if those need to be public addresses? Why not just deploy greenfield v6 in these cases? And the problem really is that since so much of the internet is v4 today, I mean, effectively all of it is, this requires you to purchase devices that are a lot like those NATs, a lot like those routers that sit in all of our houses that do 6 to 4. That are going to let the v6 customers you have deployed in your little island talk to the rest of the internet. And this is precisely how the islands I was referring to earlier get created, right? Where you've got isolated pockets of v6, such that even if the person you're trying to communicate with has a v6 address, it could be that they're just behind a 6 to 4, you're behind a 6 to 4, and there's actually no path between you. This is actually a very plausible deployment scenario, especially in these kinds of greenfield cases today. And you know, there's economic ways to look at kind of how feasible it really is to do this, where you compare the cost per port that you have to pay for, you know, that 6 to 4 NAT, the cost of the device and the ports itself. Compare that to the 1125 that you would be paying per IPv4 address, and ask yourself, where does the economics actually make sense? And of course, it'd be great if, you know, you could just kind of build tunnels of connectivity between these IPv6 islands. And if there's any hope for deployment going forward, it might be really that we just get enough of these greenfield v6 deployments going that they find it, you know, easier to peer with themselves directly and to have v6 exist there. And then we get enough of just those ligaments connecting together the islands, and we might really have a vibrant v6 network. That's one of the scenarios by which this could really work. But that transition strategy that's implied by 6 to 4, and that's implied by the dual stack approach of having IPv6 and IPv4 interfaces on the same computer, also comes up with a certain set of problems. As I said, when you have that v6 address that you've gotten from the DNS, when you're trying to contact www.google.com, you see that there's a quad A record, the DNS record that is associated with v6 addresses. Should you actually use it or not? Really, you're going to have to try it. Is what happens today. In fact, you have to see if you are connected or if you are merely just in islands. And in so doing, you're going to waste some time if it turns out that you're in islands. And the time that you waste is time that a typical web user would have switched to Yahoo rather than wait around to see if Google is eventually going to fall back to v4 and actually resolve. And this creates a tremendous disincentive to people to implement this. Such a disincentive, in fact, that Google, who has been a great advocate for v6, don't get me wrong, I think they've done a great deal to push v6 forward, they've implemented a DNS whitelisting scheme. And the way these whitelisting schemes work is that unless they have already verified, effectively pre-certified, that your v6 prefixes can reach their servers, if you ask the DNS, do you have any v6 addresses, they'll say no. Because that eyeball cost, right? They really want you to be able to connect up to them and see their ads when you make a search. And if you're not seeing those ads because you click away because your v6 isn't resolving because it turns out you're in islands that aren't connected, that's such a failure to them. They think it's worth you having to pre-certify yourself to actually be attached to them. They call this the happy eyeball problem. So there's a lot of this unhappy eyeball discussion that's gone around in the last 2 years or so. And in part, we've had trouble grappling with this because the magnitude of the problem was difficult for us to understand. We've tried this on a variety of different browsers and platforms, but the diversity of devices that are potentially susceptible to this is so large that it's not something from a governance perspective that we at the IETF can just figure out. This is something you need to actually be able to look at in the broader sphere of the marketplace to understand. We can develop, of course, fast fallback schemes or ways of parallelizing or trying to reduce the time it'll take to fall back between them to alleviate this problem. But at first, we need to measure just how bad the problem really is. And we started this actually last year in June when we held a World IPv6 Day. This was sponsored by the Internet Society, ISOC, yet another one of these ISTAR organizations, as we call them, that is associated with the IETF and the IB. The Internet Society, I guess, is really the public policy arm of this community. They spend a lot of their time working in governmental organizations and other NGOs to get good policy outcomes for the Internet, which we really try not to meddle with too much in the engineering side. But as a part of this World IPv6 Day, Facebook, Google, Yahoo, many other sites were convinced to try v6 and to see if they could detect the brokenness on the part of people connecting and then presumably advise them to upgrade their browsers. A lot of this, unfortunately, is really the IE6 problem. You know, there's so much Internet Explorer version 6 still out there. There are many kind of legacy browsers that weren't yet upgradable the way any modern browser is just automatically being upgraded. It seems like every 36 hours at this point. If you aren't part of that browser update culture, it's possible that you'll be susceptible to various kinds of brokenness. And when we looked at this, actually, we saw a brief spike in deployment of v6 that was associated with this World IPv6 Day. This shows the Alexa ranked sites on that day that actually ended up supporting IPv6, and it's a pretty huge jump. Now, again, it's a jump of virtually 0% to 3.5%, but that's not insubstantial, right? That's good. Facebook reported a lot more v6 traffic. Unfortunately, there's no actual units on this graph, so I'm not sure if this is literally 1 bit, 2 bit, 3 bit per second of v6 traffic they received at the time. But whatever it is, it seems to have been more than they were getting in the past, which is probably good. So we showed that we can at least stimulate companies to trial this, to get it out into the community so we can see how bad these brokenness problems are that we know are out there and figure out how to fix them. But still, it's apparent we're really not getting that much adoption, and that we're looking at a period of what I guess I describe as indefinite coexistence. And how to stimulate adoption is a question that, how to keep my microphone attached to my shirt is a question that is a difficult, complex question that, it's profoundly difficult. We just don't understand how to do this. And the stakeholders are, all right, I'll go back to being serious here. How to get v6 adoption, it's tough. And it's tough too because we're not the only people in this game. The people who kind of started the internet community, the IB, the IETF, the ISOC, the RIRs, IANA, there are other people in the world who think that it's probably time for the reign of the kids to end and for adults to come in and kind of take over. The United Nations has an arm called the International Telecommunications Union, or the ITU, that is profoundly interested in determining whether or not they could do a better job of administering the Internet's resources than the kind of ad hoc multi-stakeholder world that we're familiar with for the Internet. And this November, they're holding a summit about this in which a number of nation states are going to vote. At the UN, it's not like at the IETF. The IETF, you kind of have to show up and make an argument, and you either convince people that it's right or you don't. And if you don't, well, then you're just going to get shouted down. The UN, it's not like that. If you're China, you can come to the microphone and make your point, and it doesn't matter what your point is. It's going to be taken very seriously there, and it's going to have a serious impact on policy. There are alternative governance models that are being proposed for the Internet in the face of what seems like our inability to be able to affect change and things like this. And this become effectively an existential threat to the Internet being the way that it's been since its inception. And we take this very seriously. And our inability to solve this is, it's a very, very serious problem. Now, the problem is that nobody really has a better idea than v6. If anybody here has a better idea than v6, I'd really appreciate it if you can come and talk to me after the class, or right now would be great. We know that the key is adoption by the access networks, by the ISPs, the last mile providers, and of course the core providers. But there are two problems there. The one is those access networks are the people that own all the v4 addresses, as I described earlier. The people who have that investment on their books of those v4 addresses, whether they initially made the investment or not, they're worth a lot of money now. And it's a very serious problem to kind of turn your back on that. And also these access networks want to be able to provide differentiated services like the flow awareness of their NATs. And we could go into some detail if we have some extra time about kind of what the large-scale NATs are that some of these networks are looking at deploying in order to further extend the lifetime of v4. And these are measures that will buy us at least another decade, I think. And I think these measures, again, are largely motivated by the economic realities that surround v4. And we know from VHS and beta and take your pick of any other technology, the best technology does not always win in the marketplace. There are tons of reasons why we can design something that we think is really great. It's just a no-brainer. It's just like IPv4, except there's a lot more addresses. What's not to love? Yet we can't make people do it. So after World IPv6 Day, we did see a steady uptake in the number of v6 prefixes that were being advertised. And that's good. We like to see that. We see glimmers of hope. Again, as I mentioned earlier, Comcast has started deploying v6 over the access network down to the residential links. Now, if we look in some other markets, like in France, we can see 3.4% of France's IPv address residential allocation today is v6, thanks largely to one provider there who's very serious about this. About 1.5% in Japan. Companies like Telstra have made their entire backbone dual stack. These are all promising signs. If there was just some way that we could stimulate people to do what we did with that IPv6 day and just do an IPv6 turn on, like a flag day, like we're really going to do it now. Yes, Nick.
Would it be fair to say that those who are making the big change, for those for whom they would consider the amount of investment they have tied up in their IPv4 addresses is a relatively small part of their business, so it's not so threatening?
The next question is,
it's easier for them to do it.
Next question is, are the people who are making this decision people who have perhaps less of an investment in v4, who don't take their investment in v4 quite as seriously from an economic perspective? Are they the people that we see transitioning to v6? And I mean, in the case of a Comcast, I'm not sure I'd say that. I think Comcast is unusual in their interest in, I guess, the public good of the internet. They've made a number of, no, seriously, I think they've made a number of extraordinary gestures in the last couple years. And I can explain politically why I think that is, okay, if you're going to be snarky about it. But there are reasons why. But I mean, Comcast has actually made some extraordinary, I'd say, pioneering steps to kind of get to next generation internet technology. And I think they are certainly people who own a lot of IPv4 addresses. So I think they're doing it despite that reality. Now, when we look at Freenet.fr or companies like that, I think Free.fr, they actually have, I think, a different situation where they really do want to use v6 because it is cheaper and things like that. So it's a mixed bag. I think some of them are doing this for the general good of the internet, like Comcast apparently is, and then others really do have the economic incentive. So, two questions. You first.
Has it been considered, or would it ever work to charge for v6s and then allow people to trade in, allow the Comcast and Verizon to trade in v4s for v6s? To give them that incentive?
So I'm not sure I quite understand. So the question is would it be possible to charge residential customers for v6?
Like any v6 address that's distributed costs money, and then people can trade in their v4s for v6s.
Okay, so the proposal is, and I welcome proposals, right? The proposal is to actually charge people for v6 addresses and then give them the opportunity to trade in their v4s to get v6 addresses. In other words, to create an economy where v6 addresses are. So the real problem with that, I guess, is just the scarcity of v4 addresses versus v6. We're putting a very artificial pressure on the market to make v6 addresses valuable, given, again, that I can give you 18 quadrillion of them right now. It's kind of, this isn't like, Bitcoin or something, where it actually is some effort required with minting it. I mean, it's very difficult to assign a value to these things other than free. If there were some artificial way to do that, though, that's not a bad idea.
Given the fact that you started the discussion by talking about how the IPv4 address space was allocated unevenly between continents, can you imagine a scenario where the continents that have less IPv4 will transition to IPv6 first, and then you'll build these sort of smaller islands that get bigger and eventually overwhelm, I guess, North America's IPv4 dominance?
Right, so good question. So the question is, given the disparity in the allocations of IPv4 initially, well, the places that got short shrift the first time around, are they incented to transition to v6 earlier? And then basically use that to kind of see the dominance, create the big islands that might create the ligaments. We hope so. As I said, again, the example I gave of like an Asia-Pacific mobile carrier that's adding 15 million subs per year. That's a very real use case for people that I think should be v6 adopters. As I said, AppNic's already out. They were out 2 months after IANA gave out the last blocks. So these are places that have historically been under pressure and are still under tremendous pressure for these allocations. And yeah, we have a lot of hopes that in those places we'll see uptick. Is it going to be Freenet? I doubt it. Again, their remaining 3/8s are not being depleted as quickly, just because of different economic realities, I guess, in that part of the world. But in the AppNic region, I think it's quite possible. I think there was one more, 2 more, yes?
So if IPv6 addresses are so cheap, what measures are in place to stop people from grabbing huge amounts of IPv6 space and then having the same problem as IPv4?
But so the question is, what measures are in place to prevent v6 from being depleted? And the answer is there's just so much of it, we're just not even worried. we have 18 quadrillion blocks of 18 quadrillion addresses to give away.
But if they're cheap, can I not just buy a /8 of IPv6?
Good. So yeah, there have to be policies that determine. You cannot say, please give me 18 quadrillion blocks of 18 quadrillion addresses. I don't agree with that. Yeah. So, and I'm sorry for not repeating the question. The question is, what prevents you from just land grabbing these? So there are IANA policies that govern what you can actually get, and these trickle down into RIR policies as well. The base allocation you get as an organization is one of these /64s. And so you can't, if you're the Department of Defense, for example, you can ask for a lot of those /64s. But the baseline allocations are geared to be just at the /64 level per organization. Yes, so we're already in the question segment. I think you reversed. So
I know a few years ago in the adoption modeling and game theory literature, there was some work on this that suggested that the best way to spur on adoption is to provide government incentives for the carriers and the last hop carriers to adopt IPv6. And I also know that the FCC's kind of been evaluating this and thinking about possibly doing it. In your opinion, is this a good idea? Might this fix the problem? Or is it just kind of addressing part of it?
The question is, would government subsidies of various kinds help to stimulate this? And yeah, I am aware of a couple different strategies that have been looked at for that. I know that Commerce has looked at one. I didn't know that the FCC specifically had. But and Commerce is really much more involved in the address allocation dimension of this. I'd also point to the DoD has made various requirements at various times that you have to have v6 built in any products you're going to sell to them. And those have stimulated implementation, but much less stimulated deployment. And I think you see this similarly. It's easy to stimulate implementation and much harder to stimulate actual use. It's possible, though, that again, that this is a role that people could play. I think you'd find that the lobbies for the companies that are major owners of v4 would react, I think, pretty violently to that kind of intervention from the FCC or from Commerce. Just speculating there. One more, yes.
I don't know how answerable this is, but why would the DoD need multiple /64s?
Yeah.
Or even
Yeah, I think one for every molecule and every rifle that they. I tried to size this out before exactly what you could model with that many addresses. I can't give you an answer for this that's going to satisfy you. They can ask for this and receive it. So remember at the end of the day that we have some influence over what the IANA does, and the Department of Commerce has some influence over what the IANA does. And I think that if you are in good with the Department of Commerce, you can probably get an outcome you'd like from address allocation. So I only have a couple more slides here. I was just going to show a few pictures of the situation at AM6. This is roughly today. This is a couple weeks old. You can see the valleys and peaks here in a given day of how much V6 traffic is actually passing over. This is a major European peering point. This is Amsterdam's big peering point. So a lot of European carrier traffic goes through this particular piece of the internet. So you can see there are like gigabytes of V6 traffic that are moving through that particular place. It's not too bad, right? Moreover, when we did this IPv6 launch, this turn on that I was talking about around the June timeframe, it did cause the V6 volumes to actually roughly double at around that time. And again, these are still small as a percentage of what the overall traffic is in the internet, but it's getting bigger. And we think there might be a tipping point here. We think we might be able to keep pushing, and that we'll get somewhere with this eventually. And there are ways you can look at this too, where you do see increases in V6 adoption. You can always find a chart, right, that's going to back whatever point of view it is you want to espouse. But so this shows Google hits, the number of hits that they're receiving on their sites that come to them over V6, and this trend goes all the way back to 2000 or whatever, and 2009, I'm sorry, and up to 2012. And yeah, do you see a pretty big uptake on that actually, since especially the time frame of the initial V6 day and then the V6 launch this year. So it's not all bad. But as I said at the start of this, governing an internet really is kind of an oxymoron, right? Because of all the diverse stakeholders I described. And for the stakeholder situation is just, it's so complex. There are so many different forces, market forces, political forces, technical forces that are involved in a transition like this. Even if the UN did manage to butt into this, it's not clear to me what they'd be able to do with the barrel of the gun as the source of their power. Too much money is at stake in all of this. And there are no countries that are serious players in this that aren't ultimately beholden to the economy that all this is generated. And anything that endangers it or changes it or does things we don't understand to it, it has to be viewed as such a threat. People see this as just so precarious that affecting any kind of changes is profoundly difficult. Now, it may be that responsible adults will have the opportunity to take this over. I doubt it. When we look at things like V6, we can point to similar problems we've seen elsewhere, like in the domain name administration, where ICANN has become increasingly autonomous. I think I may have cut out the end of that sentence intentionally. But yes, and I just lost my chair here. There we go. Sorry. This is the end of the talk anyway, right? So I've only got 3 more words to say. But the ICANN situation, I think, is one that we look at as a model when we try to understand V6 adoption. This is terrible. Get what you pay for. And I think ICANN's situation has shown us kind of what the limits are of the power of governance, in the sense that the way that they've administered domain names hasn't been universally popular, but it certainly seems to be kind of all the system we've tried the least bad. And the problems that we've run into there have not to date ground the internet to its knees. And really the question when we look at something like V6 is, how do we proceed on this in a way that ultimately is going to preserve the qualities of the internet that we think are important, and still allow it to evolve and grow and scale and take into account more of the digital divide that we inadvertently created at the start of this. That's our challenge, and this is the kind of challenge that you all would face were you to end up in a career in internet governance doing networking at this level. And it's, I think, hugely rewarding in that you do get to work on what the fundamental problems are of the internet and ways you can make it better, and it's an amazing community of individuals. I get to interact with a lot of the people that we talk about in the course of the history of the internet, which is really cool, and they're amazing guys, and I highly recommend it as an experience.
So I guess we have about 10 minutes for questions. So
We may have gotten the question queue satisfied already there with our earlier discussion. Yes, please.
A bit more about the 64 and Toledo, like the backwards compatibility strategy.
Sure. So the question is, can I talk a bit more about 6-to-4 and Teredo and the backwards compatibility strategy? So I mean, 6-to-4, again, creates another form of NAT that sits out in the world. And it has all the same kind of dark bargain problems that NATs necessarily do. When you ask yourself what the difference is between deploying a NAT that does 6-to-4 and a NAT that just has a /10 of v4 behind it, well, the differences are actually pretty slight, except for this possibility that your island of v6 connectivity might end up being able to reach some other island of v6 connectivity eventually. Now, technologies like Teredo or any tunneling technology that lets you get out of the v4 world with a dual stack, for example, and connect up to a backbone, obviously is kind of the best case of the transitional strategy. But it still has that dependency, the unhappy eyeballs problem I was describing earlier, that when you access the DNS and find out that a site you want to reach actually has a v6 address, if they're not connected to the same things you are, you're still going to be having a problem, which is why we see things like whitelisting and strategies like that appearing. So both of these are very promising transitional technologies. Both of these are very important. Neither one has really solved the problem, though, of seeding more adoption, and both have been around now for some time.
Security of transitioning to IPv6 in that you won't really need a NAT anymore, and so you may see more computers. I don't know. So one, I'm curious, do you think you will see a lot more computers with IPs just publicly available on the internet? So like for inbound connections, that is? And if so, do you see that being possibly an even bigger problem with viruses, as I think a lot of, for Windows computers especially, if you just have access, you can get infected without any user interaction required.
Yeah, so the question is, so twofold really, will v6 do away with the need for NATs? And would it be good if it did? Because it would make all of our machines available on the public internet to be probed by whatever the best tools out there are and to infect you with various kinds of malware. And I think the second part answers the first to some degree. And that there are, although v6 was viewed for years as a way that we would finally return to the purest end-to-end model that defined the internet, that made it what it is, well, in actuality, over the years, many technologies for NATs based on v6, 6-to-6 NATs, have become part of the standards. And in part, it's just because of the operational realities that service providers want to be able to deploy in a realm where they have access to NATs. They want to be able to mask the addresses. And site local and link local addresses of various kinds were part of the v6 standards originally, but these kind of site local as the new private address space has become, I think, a part of virtually everyone's deployment story. So I suspect there still will be NATs, and that they will, to some degree, mitigate the concerns that you're describing. When we look, though, at slides of what people actually use v6 for today, and I think I may have one as a backup slide here. It might take me 10 years to find it. Let me see. I've got lots of things I could talk about here, but very good. So this is what the top v6 applications are. Unsurprisingly, 61% of it is peer-to-peer traffic. In other words, one of the reasons why people love v6, and again, this is virtually all tunneled traffic, probably Teredo, that this is modeling here, but that end-to-end peer-to-peer is precisely what people want to use it for today. So yeah, it may introduce more malware vectors than we've had in the past. Yes.
So a remote student asked this before your talk. Is this a 5-year problem? Like, will we have IPv6 in 5 years, 10 years, 20 years, 50 years? Like, it's certainly complicated, but if you had to guess, gun to your head, when you would think the IPv6?
So this isn't being broadcast around the world, right? Right, so I do think that, I referred briefly earlier to the large-scale NATs that some carriers were looking at deploying at the new /10 of private address space. It's been allocated specifically for these NATs. I think this will buy v4 at least a decade of lifetime. It could be more. The point, a decade is a long period of time to devise other ways to keep v4 alive, too. So, I mean, I would love to be wrong about this. I really would. I mean, and it's possible some people are going to come up with stuff that we just have not considered that is going to stimulate more v6 adoption. And the steps that have been taken have been having an impact. We have been seeing increases and the amount of v6 that's out there, and the number of advertised prefixes, the number of hits to the sites that are from v6. So it's possible we'll reach a kind of tipping point here, and this really will start to evolve. But what I know we can't do much that's going to make that happen, right? I'd love to be able to tell you, well, our plan is to do 1, 2, and 3, and then I'm sure we're going to have v6. But yeah, that's not how it works.
So if I understood the point before, we're at a point right now where all the access networks, the internet service providers, we've distributed all of the IPv4 addresses, but these service providers still haven't distributed them, like all the ones that they have, to customers. They're still like underutilized in that sense. The question is, would you rather like surge in devices that are going to be connected to the cloud with smartphones, tablets, and so forth? Then, and you mentioned before that it's against their interest right now to switch to IPv6. So with the rise of like devices, do you think they're at a point where it'd be more cost effective for them to move to IPv6 so they can support more devices?
So long question. I mean, the question really was, will IPv6 effectively be cost effective enough for the carriers that are deploying many new devices? It'll be worth their time just to move to that rather than relying on their v4. And I think for some carriers, it may very well be. Again, the examples I gave of carriers who are radically growing, and this would be people in India and China that are just signing up so many new subs per year. For them, the economics of this may actually turn out to go that way. Even comparing, the costs of 6 to 4, the cost of all the things they'll need to actually make v6 addresses work, it's very possible that it will for some of those carriers if they get serious about fielding it. But it's going to be people who are radically increasing their subscriber base, and that means there's going to be some specific areas of the world. And as it turns out, those are areas of the world where v4 is already very scarce at the RIR level. That people like AppNic are just out already. So that combination, that confluence of circumstances may lead to precisely what you're describing. And that's a story, right? That'd be great if that's how this all played out. So in the very back, and then you.
We talked a lot about the economic challenges of IPv6, but since so many devices can already support IPv6, are there any real sort of big technical challenges that prevent us from just implementing that?
So the question is, we've talked mostly about the economic challenges facing v6. Are there any remaining technical challenges given the wide deployment of this in devices? And the happy eyeballs question that I was talking about the consequences of dual stack in particular, although much of that brokenness has been weeded out by what we've done in the last couple years, that's a pretty recent development, right? I think we're starting now to see enough traffic that we're understanding better where there are technical limitations still. I don't think we've completely understood all of them. I think the bigger this gets, though, and the more deployed it gets, the more we're going to see if there's things that we've missed to date. In general, though, I'd say no. I don't think that the challenges are technical in that sense. There may be some gotchas like the unhappy eyeballs thing that are still out there. But I suspect it's going to be much more about the administration than it is about the technology at this point. I mean, the technology is the same technology as v4 with more addresses, right? It's really not radically different. We can talk about site local and things like that. But yes, there are differences, but they're not radical differences. Thank you, Edwin.
So in terms of changing the incentives, there's been an economic argument for getting rid of the problems of patents blocking innovation by having governments buy out patents. So do you think a similar system could be useful for incentivizing these holders of large IPv4 spaces to release them if the government just directly buys out?
So what would it cost to buy out the v4 space? Let's say 188 million per /8, so 256 of those. Somebody here must be mathematically inclined enough to 50 billion.
That's less than the auto industry.
A bailout is what we need. This is the best idea ever so far.
And with that, let's